Good morning, everyone.
Yeah, good morning, President Eden.
Good President. Good morning, Professor.
Yeah, good morning, Professor Cheng.
Good morning, everyone.
Good morning.
Good morning, Professor Brigitte. We've been in touch these days through email. Good morning.
Hi, good morning, everyone. Welcome to the third water recruitment. Last time we have a second one, and last time we talked some problem. It's about the water shortage, water pollution, human health, and this time is the third virtual workshop. This topic is the climate change, water resource and ecosystem challenges and opportunities. Climate change is expected to have a dramatic effect on water resource and ecosystem, and in turn threat the livelihood and human health eventually. Higher water temperatures and changes in extremes, include flood and droughts, are projected to affect water quality and exacerbate many forms of ecology degradation. On the other hand, the study of climate change, water resource, and ecosystem are undergoing a revolution owing to the development and application of a diverse range of new technology and methods. However, its latest technologies and methods are still supported by relatively limited scientific evidence. There is an increasing need of understanding of how climate change affects water resource and ecosystem. The workshop on climate change, water resource, and ecosystem challenges and opportunity seeks to create such a platform to review and present the advanced methodologies, current progress and challenges, future opportunities in water ecosystems management and climate change. And today I'm honored to invite 4 host organizations. And today I want to invite the Prof. Chen, as Dean of College of Water Science, and the President of AIT to talk something to us. Hello, Prof. Chen.
Hi.
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 Would you like to talk some sentence for us?
Yes. Dear President Wong, colleague and friends, good morning. I'm Hong Guangcheng from the College of Water Science, Beijing Normal Universities. And it's my great honor to attend the third AIT-BNU joint water workshop on climate change, water resource, and ecosystem challenge and opportunities. Above all, I would like to give a brief introduction about our university and college. BNU, a key university under the administration of the Ministry of Education, is a renowned institution of higher education known for teacher education, education science, and basic learning in science, arts, social science, and engineering. The College of Water Science was formally founded in 2005. Since then, the CWS has always been academic-oriented and actively adapt to the needs of social development with focus on fostering of students' research ability, practice ability, and team spirit. In the past few years, BNU and AIT has arranged meetings and workshops. In 2018, Professor Wang invited Professor Sangam to arrive BNU and participate in academic exchange activities in 9 days. During the workshop, experts discussed how climate change and the land use influence on water qualities. Similarly, AIT invited BNU's professor to look around the university and talking about the students' training and the students' exchange between the two universities. It was a foundational for both sides to reach a cooperation consensus. Last year, we successfully take a second AIT-BNU joint virtual workshop with the efforts of Professor Xue and Professor Wang. The COVID-19 could not stop the communication between us. As we know, the rapid development of economic urbanization and population growth pose a large pressure on water-related issues globally. Thus, last workshop paid attention to hydrology and water science, the water shortage, and extreme precipitation events, such as what happened in this summer in Zhengzhou, caused either by the natural or anthropic factors, has a large impact on the global ecosystem and freshwater sustainability. In turn, the water shortage, water pollution, and together with the degradation of ecosystem may threaten the livelihood and human health. Reporters in this workshop shared ideas and attract more talents focused on this problem. Today, third virtual workshop is going to discuss what climate change impact on the hydrology and the water science, ecosystem and environment. We are looking forward to catch some solution and measures to solve the problems and the challenge. Furthermore, it provides a good chance and platform for the communication on the state of the art regarding water health ecosystem management. It would surely contribute to the advancement and improvement of water management for Thailand and China too. I'd express sincerely appreciate for all outstanding experts and professors to share the presentation for us. Workshop invited many talents who worked on the hydrology and water source and ecosystem and environmental area. They published many contributions and research achievement. It promoted the development of relevant field research. It is a great honor for us to attend a virtual workshop, which will give us a deeper understanding of water science. We are looking forward to discuss the challenge and opportunity to solve the water and ecosystem problems. We have always maintained a very good friendship and hope that the event can promote our further cooperation. Again, I wish a successful and fruitful workshop today and look forward to further communications between us. Thank you very much for your active participation in this virtual workshop. Thank you, everyone. Bye. Thank you.
Thank you, Prof. Chen. Now, I would like to mention that Prof. Chen as Dean of College of Water Science since 2019, but 3 years ago, Prof. Chen was Director of International Exchange and Cooperation Office of Beijing Normal University. Thus, Prof. Chen experts at international exchange activities. He played an important role in promoting the international cooperation with AIT, such as student exchange and academic cooperative research. Meanwhile, Prof. Chen's research area are environmental health impact survey, no point source pollution, water pollution control, and environmental impact assessment. We are glad Prof. Chen to attend our virtual workshop today. Next, I would like to invite Dr. Adam Wu to talk something. Dr. Adam Wu is the president of Asian Institute of Technology. He also served as a special advisor to the Shaw Foundation in Hong Kong. The Shaw Foundation was funded education projects in Greater China and elsewhere for over 30 years, and is the sponsor of the world-renowned prestigious Shaw Prize in mathematical science, life science, and medicine, and astronomy. He was most recently the vice chairman of AIT-BNU Group Asia. AIT-BNU Group, based in Berlin, is one of the world's leading environmental engineering and services companies. Could Edwin Wood talk something with us? Hi.
Yes. Good morning, Professor Chen Hongguang, Dean of College of Water Sciences in Beijing Normal University, distinguished guests and participants of the workshop. I'm pleased to welcome you all to the third AIT-BNU virtual workshop on climate change, water resources and ecosystems, on challenges and opportunities, jointly organized by Asian Institute of Technology, AIT, Beijing Normal University, Hefei University of Technology, and Beijing University of Technology. I'm happy to note the continued collaboration and extension of the partnership beyond AIT and BNU at this time. 在这里，我跟我们中国朋友说一两句，希望你们昨天过了一个很愉快的中秋节，大家都知道16的月亮比15圆，所以今天我们应该有一个非常好的一个活动。Water is at the core of sustainable development. It is critical for social economic development, healthy ecosystems, and for human survival itself. However, it is evident that climate change, together with rapid population growth, land use changes, rapid urbanization, pollution, and damming of rivers, all threaten the sustainability of water resources and ecosystems, and consequently, sustainable development. Understanding the connection between water, climate change, and ecosystem services becomes the key to achieve the global water security. Water and climate change themes are at the heart of AIT. It is reflected by our education, research, and outreach since 1959. The water program is the first program established at AIT. We're offering several education programs, several dual degrees, and conducting cross-cutting research on climate change and water resources in the Asia-Pacific region and beyond. In fact, water is one of our 5 strategic focus areas. Climate change is one, infrastructure, technology, policy and society, smart communities, and food, energy, and water. AIT is ranked 15th in the world in the prestigious Times Higher Education Impact Ranking 2021 for our work to end poverty. In line with the UN SDG goal SDG 1, no poverty. Work on 4 other SDGs also position AIT in the global top 100. The THE impact rankings measure how universities worldwide are performing against the United Nations Sustainable Development Goals, a key focus of AIT. I learned from the program schedule that there are 32 presentations by researchers from more than 30 academic and research institutions. The presentations belong to some very important themes, such as modeling changing climate relating to the hydrological cycle, climate extremes and impacts on water resources and ecosystem, interactions of water resource and ecosystem, and risk assessment of ecosystem degradation in a changing environment. I'm hopeful that the presentations and deliberations will generate some new knowledge to address the challenges such as climate change and its impact on water resources and ecosystems. I'm also happy to learn that the organizing committee is planning to publish a special issue on climate change, water resources, and ecosystems, challenges and opportunities in the peer-reviewed international journal as one of the outputs of the workshop. I also take this opportunity to express my wish to collaborate with all of you and your institutions in developing joint academic programs and projects in AIT's 5 thematic research areas, and together we can promote what AIT's motto says, social impact with innovation. Finally, I would like to express my sincere gratitude to Professor Sangam from AIT, Professor Wang Guoqiang from Beijing Normal University, Professor Zhou Yuliang from Hefei University of Technology, and Professor Wu Jing from the Beijing University of Technology for their wonderful and hard work and collaboration. And I wish you all for a fruitful workshop. I hope that the 4th virtual workshop, we can take away the word virtual, and I can personally welcome you to AIT. 希望能够在亚洲理工学院下次见面，谢谢大家。
Thank you.
Thank you, Dr. Adam Wu. I'm so sincerely appreciate the Dr. Wu and Prof. Hong-Guang-Chen to give us the best wishes. Now, today, I feel honored to share the wonderful time with you. In the morning, our workshop separated the 2 conferences. The session 1 is modeling changing climate relating to the hydrological cycle. Another one is the session B, climate extremes and impacts on water resources and the ecosystem. In the afternoon, we also separate the 2 conferences. The session 1 is interactions of water resource and the ecosystem. The section 2 is a risk assessment of ecosystems degradation in a changing environment. Thank you everyone to attend the virtual workshop. I hope everyone enjoyed today.
Yeah, Macy, can we have a group photo? We have a photo session before the parallel session, right? Yeah. Yeah, Mr. Ruel, are you there?
Yes, sir.
So let's have a group photo. Yeah.
Yes, sir. So good morning, everyone. Could you please turn on your camera and smile for the photo group? So we have the 3 screen. So the first screen, please turn on your camera again.
请我们大家把那个摄像头打开，然后我们拍一张集体照。谢谢大家。
Okay, thank you, Dr. Wong. Okay, for the first screen, smile. Second screen. For the second screen, please smile. Okay, thank you for everyone.
Thank you.
Thank you. 谢谢大家。
谢谢大家。
Yeah, thank you, Mr. President and Professor Cheng. Thank you very much.
Thank you.
I hope today this picture is really, really pretty. So, hi, Sangam. Could we start the conference? Or...
Right. Yeah, thank you, Macy. As you rightly mentioned that we have the parallel session in this morning, right? This session A1 and session B1. I hope all of you have these programs scheduled with you. So if some of you wants to stay in session A1, you can still remain here. But if you want to listen to session B1, you have to switch to another Zoom ID and password. It's already in the program schedule. So if you are planning to attend session B1, which is climate extremes and impacts on water resources and ecosystem, please log in into another session, yeah, session B1, okay? So I'll give you a few minutes to decide which session you want to stay, right? We have session A1. If you want to stay here, you can stay in the same meeting. And if you want to go to another session, session B1, which is climate extremes and impacts on water resources and ecosystem, you have to switch to another Zoom meeting room. Yeah. I have already uploaded the latest program schedule. If not, then maybe I will again text you in the chat if you would like to switch to another room. Yeah.
Thank you, Sangam-san. Messi, please, let our participants, participants from China, to know we have two sessions, A1 and B1, also A2, B2, and we can, encourage them to, to participate maybe time to time from A1 to B1, and to, just to follow what they are interested research works. Thank you.
Right, I am writing in the chat box also.
Okay.
This is for session A1, right? And we have the session B1. I will put the text in the chat box.
Okay, thank you.
This is B1. Yeah. So everyone, please look at the chat box. There is another session, session B1. So if you'd like to switch to another session, so please log in into this Zoom ID and meeting link. Okay.
Shall we? Shall I? Explain a little bit in Chinese?
Yeah, please, So Wang San.
OK， 各位各位老师、同学，大家好。我们上午的致辞之后呢，我们整个会议会分成两个平行会场，一个是大家可以看到的，就是 A1 和 B1，A1 和 B1是不同的 Zoom 号。然后现在我们的这个 Zoom 账号是 A1 的账号保留，然后请大家根据汇报的情况选择进 A1 或者是 B1 的那个 Zoom 账号在会议通知里能找到。然后感谢大家，请大家可以穿插着去听一听 A1 和 B1 的相关的汇报感谢。OK， Sangam-san.
Yeah, thank you, Wang San. Let's wait for a few minutes. Probably they will be switching to another Zoom meeting room. Yeah.
Okay. Messi, Messi.
Hi, yeah.
Maybe you and Miss Lee can both you two can chair can chair the two sessions each one and responsibly. So this will be convenient to organize the whole day sessions.
Okay, I will stay this conference. I will be prepare, and Li Hui will go to another one. We will get together to managing all the workshop. Yeah.
Okay, thank you very much.
Thank you.
Yeah, once again, I still see there participants in this meeting room. So if you are finding difficulty to switch to another room, so please feel free. Please take some time to go to another session. Yeah, the another session, session B1, is chaired by Professor 𝐕𝐢𝐫𝐁. Okay, so welcome to this session A1. This session is titled as Modeling Changing Climate Relating to the Hydrological Cycle. I'll be chairing this session until the launch time. And this session consists of 6 presentations, and they will be presenting the research they have conducted in at least 4 countries. So may I request presenter to identify themselves. We have 6 presenters. So Professor 𝐕𝐢𝐫-𝐁𝐍𝐔, are you there?
Yeah, Professor Sangam, morning.
That's good. So we have Libo Wang, are you there?
Yeah, I'm here.
Okay. We have Mohammad Latif Hussain. Latif, are you there? Okay, so he might be joining very soon. Manish Shrestha. Manish, are you there? Okay, so he might be joining also very soon. Professor Arup Kumar Sharma. Okay, so I haven't seen him. Ching Fang, are you there?
There.
Okay, maybe some of the presenter will be joining very soon. So now we can start this session, but I would like to give you a few guidelines about this session. I would like to request each presenter to have presentations about 15 minutes, okay? And then I will have the question and answer session at the end of this session. So may I request the first presentation from Professor 𝐕𝐢𝐫𝐁. So he will be presenting about contribution of base flow non-point source pollution for a typical agriculture intensive basin in northern China. Professor Sui, it's your time.
Yeah, thank you. Can everybody see my screen?
Yes, we can see it.
Works well? Okay.
Yeah, Professor Sui, maybe you can make it as a PowerPoint presentation. You can zoom it.
Yeah, sure. Yeah, okay. Hello, morning, everyone. Good morning, everyone. My name is 𝐕𝐢𝐫𝐁, and I'm from Beijing Normal University. Today, I will present research entitled by Contribution of Base Flow Non-Point Source Pollution for a typical agriculture-intensive basin of northern China. As you can see from the title, here I will to give you a short introduction about my research in northern China concerning the non-point source pollution. In detail, I will focus on the base flow, as I will explain in the following. My presentation contains four parts. First, it is the research significance and the research objectives. As we know, base flow is an important component of the hydrological cycle. Knowledge of base flow hydrology have improved our understanding of the watershed processes and the relationships between human activities and the ecosystem functions. In many areas, base flow maintains the basic functions of the river, but it also leads to deterioration of water quality, especially in basins with significant groundwater contamination. As we know, the overall runoff is composed of two parts. First, we call it the surface flow, and then the base flow. Studies have indicated that highly drained agricultural watersheds with a very high ratio of base flow to the total river runoff. In China's coastal agricultural watersheds, basins, research on non-point source pollution has mainly focused on pollution caused by the surface runoff. But other contributions, from the non-point source pollution, such as base flow, has not been adequately analyzed. In this study, as I said just now, I will focus on the non-point source pollution from the base flow. And in this case, I selected a very small basin, the basin which is intensively agriculture cultivated. And the research questions from my research were assess the spatial and temporal variability of base flow non-point source pollution at the subbasin level. In this case, I will to investigate the contribution of base flow and the base flow non-point source pollution to the total river runoff. And then I will investigate the spatial and temporal variation characteristics of the base flow and base flow non-point source pollution. The third one is that I will then investigate how the basin area will influence the non-point source pollution. In other words, I will investigate the scale effects on the base flow contribution to the total non-point source pollution. In this way, we hope we can construct a scientific and efficient base flow non-point source pollution estimation method, which can be applied to the small agriculture intensive basin. And then I think this research can contribute to provide a clear reference for the management of environmental and water quality management here. Then I will give you a short introduction of my research area and the method I used. This is, as I said, this is a very small basin in northern China. So this is the Shandong province, and then this is the basin where it is located. as you can see, this is a small basin which is near the sea. The annual average temperature of this basin is 12 to 14 degrees, and the precipitation is around 500 to 760. The total area of the basin is very small, around 650 square kilometers. Also, the river length is around 70 kilometers. There are, as you can see, there are two main tributaries here. We measured the water quality from 4 sections on the river. And as I said before, this is agriculture intensive basin, so most of the land was covered by the croplands, mainly cultivated by lands, and the main excess pollutants are total nitrogen and total phosphorus. The main pathways of non-point source pollution was livestock breeding, the fertilization, and the rural living pollution. This is a simple flow chart of the analysis. Overall, this study can be divided into 3 steps. In the first step, we first use the digital filter method to derive the base flow, and then we also use the soil and water assessment tool, that is the SWOT model, to get the base flow, and then to investigate its spatial and temporal variations. And then the concentration ratio coefficients calculated by the digital filtering method and runoff data are used to calculate the total nitrogen and the total phosphorus loss of the base flow by the SWOT model. Finally, based on the spatial and temporal distribution characteristics of the base flow, the dynamic changing characteristics and the scale effects can be analyzed. First, I will give you a short introduction on the explanation of the pollutants, because we have the runoff data on a daily scale, while the water quality monitoring data, the water quality data, is on a monthly scale. So first, I used the LODIST model to interpolate the monthly data to the daily data. I use the LODST model. First, I will get the I will calculate the total pollutants, and then we will get the we estimate the equation function, the parameters, and then we will test the accuracy of the model. As you can see, this is the last results we get, which we will regress the total loss explained by the runoff and the time. And you can see from the results the coefficient of determination, the series correlation coefficient, and the PPCC shows that the accuracy of the results can satisfy our following research. Then I use the digital filter method to conduct the base flow segmentation. This is the method used very much in the literature. We also call the Eckhart method. As we can see, this is the base flow, and this is the total runoff. And also, we can use the spot model to get the base flow too, and according to this equation. Because there is no accurate method to get the base flow, so we can verify by the results by the two methods. Similarly, we can also get the non-point source pollution results from the same method, and then we get the base flow index and the contribution ratio from the Ludist model to validate the spot model, and then we can get the base flow over a large area. Okay, the results section. First, we validated the model with the runoff data, and on the basis of the spot model simulation, we found that the watershed, there are 3 parameters are sensitive to the simulation of the water quality. That is the organic phosphorus enrichment rate in sediment. And the second is the denitrification threshold for soil water content. The third is the organic state nitrogen decomposition rate coefficient. And then we validated these 3 parameters, and then we found the model can generally simulate the water quality well. Here, I want to mention that the model can simulate the runoff better than the water quality. Usually, if the R square, I mean the determination coefficient is above 0.5, we will say that the water quality simulation can meet our requirements. And then we investigated the characteristics of the dynamic changes of the non-point source pollution in the watershed. Based on the simulation of the basic non-point source pollution by the soil and water by the spot model, we can derive the dynamic, spatial, and temporal variation characteristics of the basin. First, for the temporal characteristic of the non-point source, the interannual variation of the total nitrogen and total phosphorus pollution is positively correlated with runoff and rainfall. Besides, the non-point source pollution output changes show a clear seasonality, which is higher in the flood season than that in the dry season. You know, this is this is in Chinese. This is the total nitrogen, and this is the total phosphorus. This means the winter, autumn, summer, and spring. Also, for the spatial distribution of the non-point source pollution, we found that the interannual variation, pollution loss is shows that it is low in the northeast. It is smaller in the northeast, and it is higher in the southwest. You know, the areas with high values of pollutants is mainly dominated by croplands, and the output intensity of the non-point source pollution croplands in plain areas is greater under normal water. under normal water supply conditions. Also, we focused on the temporal characteristics. We found that for the interannual variation of the base flow, total nitrogen, and total phosphorus, the contribution of the base flow to the total runoff pollutions has decreased extremely significantly in the year with sufficient water. That is in the year 2008. As we can see, the contribution, this is the contribution ratio. It is much smaller in 2018 and larger in the year of 2016, which is a dry year. And the intra-annual temporal distribution was characterized by the higher in the flood season and lower in the dry season, which is consistent with the intra-annual trend of the total runoff pollution. You know, this is the annual scale, and this is the monthly scale. As we can see, the total pollutants was higher in the summer seasons. Also, we investigated the base flow indexes and the total nitrogen contribution rate of the base flow. Also, the total phosphorus contribution rate of the base flow. We found that the spatial distribution characteristics of the base flow index and the contribution of base flow pollution are basically the same. This is for the flood season. This is for the dry season. And we found that the spatial patterns of the two seasons are similar. This is showing a spatial distribution of high in the east and lower values in the west. And also for the contributions of the base flow of total nitrogen and total phosphorus, the source areas of rivers, which is less affected by the human activities. I mean, for example, in the northern areas, is with relatively good soil and water conservation, relatively low loss of the non-point source pollution load. However, the other subbasins, by the small amount of water in the river, was intensively intensively impacted by the human activities, serious soil erosion, and many other factors. The pollution contribution of the base flow is at a high level, which is similar for the total phosphorus. Sorry, there's something wrong when I open the camera. Okay, also at last, we investigated the scale effects of the base flow and the base flow pollutions. We investigated three variables, which is the CV, the contribution ratio, and the base flow index. We found that the impact of precipitation on base flow non-point source pollution in the watershed is decreasing as the spatial area increases. So this is for the different months, and we found that the watershed, the basin area has a large impact on the base flow non-point source pollution. And also the mean values of the base flow total nitrogen and total phosphorus, that is, the contribution ratio, increased with the increase of the spatial scale, and the contribution rate was higher, indicating that the base flow is an important pathway for the transport of the non-point source pollution during the dry seasons. And similarly, the average base flow index for all the different basin areas it is greater than 0.5. This means that the base flow in the region contributes more to maintaining the total runoff. And also, the response of base flow to rainfall is more stable when the basin area is large. Okay, the take-home messages. We found that the non-point source pollution in the basin shows significant spatial and temporal contribution characteristics, and higher in the flood season, rainy season, and lower in the dry season. And we found that the base flow non-point source pollution contribute a lot, and which is shows significant relationships, positive relationship with the runoff. Especially the spatial distribution of the contribution rate in the flood and dry season are basically the same, similar with a similar pattern, showing the characteristics of high values in the east and low values in the west. And last, the amount of the base flow and non-point source load of the base flow increased significantly as the sub-basin areas increases. And also the base flow index and non-point source contribution generally increased. And the impact of precipitation on the base flow are decreasing with the expansion of the basin area. Okay, thank you very much.
Thank you, Prof. Xu Baoling. The next one is Li Bo Wang and Guoqiang Wang. The next one is talk about identification of influencing factors of evapotranspiration and the quantitative analysis in cold and area regions. Is that right? Hello, Li Bo Wang. Can you hear me?
Yes, I can. Yes, I can hear you.
Could you start your presentation?
Okay, I will share my screen.
Yes, please.
Okay. Good morning, everyone. My name is Wang Libo and now study in Beijing Normal University. Today, I'd like to share my study about identification of influencing factors of evapotranspiration and its quantitative analysis in cold and arid regions. In this presentation, I'd like to focus on recent developments in eco-hydrological, and I'll speak for about 50 minutes to allow time for questions and comments. Now I will start the presentation. The IPCC report shows that the global average surface temperature has raised by 0.74 centigrade in the past 100 years, and it has risen by 0.65 centigrade in the past 50 years. The warming rate of the latter is almost twice that of the former. Okay, I will open my camera. Sorry. Oh, sorry.
Yeah, Wang, I think if there is some internet issue, probably you can turn off your video and make a presentation. Yeah.
Yeah. Please wait a minute. I will. I'm now in my dormitory because the environment is very quiet. So it's a little bit mess. Okay, okay, I will continue my presentation. Okay, I will start. The warming rate of the latter is almost twice that of the former. In China, the temperature has. I'm sorry. In China, the temperature has risen by the temperature has risen by I'm sorry, because of the camera have some problem. I can't see the screen when I open the camera.
Right. So you can turn off your video, Wang. No problem. Yeah, please.
So I have to shut off the camera. I'm sorry. In China, the temperature has risen by 0.5 to 0.8 centigrade, and the variation of precipitation functions is insignificant over the past 100 years. Global climate change affects atmosphere water vapor content and atmosphere calculation, leading to the significant changes in water calculation systems such as precipitation and evapotranspiration. At present, under the influence of global climate change, there are some phenomena such as increasing temperature, decreasing rainfall, changing vegetation, distribution pattern, and so on. Driven by this long-term climate change dominated by temperature rise, vegetation succession occurs in grassland ecosystem in cold and arid areas, which leads to the disorder of hydrological process and water budgets in bringing advanced efforts such as grassland degradation and reduction of specific diversity. From the long-term research, the impact alteration of watershed hydrological process change often focus on the direct impact brought by climate or vegetation dynamics, while ignoring the both of the function of them. So what are the key hydrological factors affected by vegetation dynamics driven by global climate change, and how strong it is affected? This is the focus of this study. Vegetation is an important factor affecting the eco-hydrological process, and its change law has a direct impact on the whole basin. Through the analysis of probability sampling method, it is finally determined that 60% of the observed land changes are related to human direct activities, and 40% are caused by indirect driving factors such as climate change. NDVI in global air areas showed a very significant upward trend. Global warming intensifies the abnormal change of evapotranspiration, which is bound to lead to the change of water cycle in ecosystem. Therefore, the simulation of evapotranspiration and the identification and the identification analysis of its key influencing factors are particularly important to explore the law of eco-hydrological change in the basin. Evapotranspiration is an important process of ecosystem water balance and energy balance. Vegetation transpiration and soil water transpiration are controlled by different biological and physical process, and are the two main components of evapotranspiration. Now, the main methods for measuring evapotranspiration include mode estimation based on water balance method, Baldwin specific energy balance method, and direct measurement based on transpiration meter method and EC method. Evapotranspiration modules based on statualized remote sensing can be divided into parts. And in this study, I have tested the air relative humidity based two source evapotranspiration module was developed to explicitly consider both plant transpiration and soil evaporation. And this module named Shuttleworth-Wallens module. And my study, I chose the same arid typical grassland area, Hailar River Basin, which is located in the southwest of Ulaanbaatar in the Mongolia Autonomous Region, with a temperate continued climate. And because of the specific climate conditions and spatial differences make the basin have complex and diversity ecosystem communications, which are sensitive to climate change. Resulting in a series of ecological problems. Among them, land creation and vegetation coverage reduction are more significant in this study. At this stage, the study in Hailar River Basin found that the drought in this area has continued to identify in recent 20 years. The richness and diversity of dominant species in the region have decreased. The dominant species with single and degrade community comparison has been transformed into drought-tolerant species, and the vegetation coverage in the study area has also been transformed. The water cycle elements under vegetation change, like the dominant factors of evapotranspiration, are different under different environmental conditions. Vegetation plays a regulatory role in watershed evaporation. Therefore, according to the above work and carried out in the region, it can be recognized that vegetation system is an effective regulation and storage tank of hydrological process. Reviews the impact of its structure and function change on hydrological process and explain eco-hydrological systems of soil water change and evapotranspiration process. And under the background of climate change, what key hydrological process have been changed by vegetation change in grassland ecosystem in cold and arid area, whether this change will provide regional eco-hydrological problems is not only an important content to review the impact of global climate change, but also the basics to support the stable development of watershed SPAC system, which is of great significance to the regional of the water resources. And in this study, I have two questions. First one is how to solve the large-scale petal temporary continuous hydrological elements. I have functioned the 𝐵𝐺-MC module in this area, and it's the 𝐵𝐺-MC module is a great distributed hydrological module based on digital elevation, and I have great interest about this about it coupled with Shuttleworth-Wallen's module, water vapor source module. It is suitable for the underlying surface with sparse vegetation. And the simulation results of Hailar Station show that the NARSH efficiency is more than 80% in the regular rate, and the performance is good. The evapotranspiration simulation results is merely realized by comparing the observed values of correlation system with the module simulation. And the evapotranspiration and measured data is significant, including in the Mongolia Ecological Research Station and Baker Step sample pot. The NARSH efficiency coefficients between the simulated and observed values are over 85%. and the results shows that the BTOP MC module can estimate more accurate evapotranspiration. And next is the question 2, how to qualification of impact institute of key hydrological process under climate vegetation change. And I use the structure equation module. And it is an effective tool to analyze the relationship between potential variations and observation variables. Now the results, result 1. Through the BTOP MC module, we can have the hydrological, we can obtain the continuous evapotranspiration in the study area from 1981 to 2017, explores the correlation of variation factors to evapotranspiration through second order particle correlation analysis and relevance the variation laws of evapotranspiration in the study. And the result 2, impact analysis of climate factors. After the analysis, I found the main factor leading to evapotranspiration changes were identified by comparing the continuous of factors and vegetation leaf area index. Temperature and precipitation are the main factors causing evapotranspiration changes in the whole basin. And the decrease of precipitation that results in the decrease of evapotranspiration. Precipitation and temperature are the main factors affecting the seasonal variation of evapotranspiration in the basin. The combinations of precipitation in winter and spring are negative, which indicates that the contribution of precipitation to evapotranspiration decreases significantly with the seasonally limited precipitation. Well, those of precipitation in summer and autumn are positive, which indicates that the combination of precipitation to evapotranspiration increasing significantly with the increase of precipitation. And then I have some study about the effect of the temperature to influence the evapotranspiration. In this study, I also find the change of evapotranspiration is controlled by evapotranspiration potential, soil moisture, and vegetation status. It is a reflection of evapotranspiration capacity and regional water condition demand, in which the impact of environmental factors is particularly important. In this process of hydrological cycle, temperature is an important environmental factor other than precipitation. According to the above analysis, the asthmatic warming phenomenon under the background of global warming is mainly caused by the faster warming at night than during the day. It can be seen that the particular correlation coefficient between evapotranspiration and the highest temperature in both growing season and non-growing season is positive. In non-growing season, expect that the particle correlation coefficient of the lowest atmosphere temperature is negative. The others are positive. And surface and therefore, compared with the nighttime warming, the breeze of daytime temperature will have a greater impact on surface evapotranspiration by increasing vegetation physical activities. And temperature will also affect the soil moisture through evapotranspiration, and then indirectly affect the physical process of vegetation. In dry climate areas, due to the extent of water stress, with the increase of temperature, evapotranspiration will strengthen and soil moisture will decrease, resulting in water loss, weather and including raising in water loss and even depths of vegetation, which will inhibit evapotranspiration. Therefore, the negative feedback effect of estimated warming on evapotranspiration in arid and semi-arid areas is significant. In the range of more precipitation, the rise of temperature has an inhibitory effect on evapotranspiration. And in this study, I find that the effects of different types of the temperature on evapotranspiration are significantly different in growing season and non-growing season. Overall, the change of evapotranspiration is merely dominated by the highest temperature, and most of them show positive effects. The conclusion remains the same in the change of atmosphere temperature and surface temperature. And that's all my presentation. Thank you.
Yeah, thank you, Wang. It's very nice to see that you have also used this BJUT model for your study.
Yeah.
I and Professor Wang were also involved in the development of this BJUT model when we were together in Yamanashi University in Japan. It's great. Okay, thank you very much. I'm sure all of you have questions, but I would like to suggest you put these questions at the end of the session. We will have the question and answer session. Okay. So now I would like to invite another presenter, Mohammad Latif Hussain. So he will be presenting his research on statistical downscaling of current and future climate data sets under heterogeneous terrains. Latif, are you here?
Yes, sir. I'm here, sir.
You have about 15 minutes. You can share your screen and start your presentation. Thank you.
Good morning. I think all of you hearing me. Excuse me.
Yes, we can hear you.
Okay, thank you, sir. Good morning to all, and welcome to my presentation. My name is MD Latif Hussain. I am from Bangladesh. I have completed my master's from AIT, and now I am in a job in LGD, Bangladesh. This is my research title, Statistical Downscaling of Current and Future Climate Dataset under Heterogeneous Terrain. Climate. Climate is defined as average weather. Climate change is long-term weather change. Climate change impact. And for climate change, we are facing a global warming and problem for water availability and some other issues also. Climate change scenarios. There are some scenarios which is to predict the future climate, and for some observations, those are RCPs and SSPs. Here's some statistics from IPCC that our global temperature is rising for RCP different scenarios, and in the different part of the world, the temperature rising is different. Climate models. To evaluate the climate, their scientist has developed some different kind of models, GCMs and RCMs. GCMs are larger scale model, and RCMs are comparatively less finer resolution models. And downscaling. Downscaling is actually for local area need, for local area climate change model, we need downscaling for analysis the local problems. So downscaling is required, and there is two types of downscaling, that is statistical downscaling and dynamical downscaling. And in this presentation, my thesis was objective was to develop fine resolution precipitation and temperature, to develop a fine resolution precipitation and temperature variable for impact assessment studies by statistical downscaling approach. Specific objectives was to develop a lab state incorporated spatiotemporal regression-based statistical downscaling approach to downscale climate dataset at monthly time scale for rainfall and temperature, to evaluate the performance of this multilinear regression based lapses based model against standard existing temporal statistical downscaling models, to develop fine resolution future downscaling, to develop fine resolution future downscaled monthly rainfall and temperature from RCM dataset. This is the area which I worked for. This is the Wang Basin. It is northwest part of Thailand, and there are three provinces: Chiang Mai, Tak, and Lamphun. Total area 26,289 square kilometer. And here there is the highest peak of Thailand, and that is 2,565 meters. We have taken two weather station data, that is Chiang Mai and Tak. And here you see it is a heterogeneous area, and there is a significant elevation difference in this area. In this thesis, we have we use different data, just like for meteorological station data of which is converted to from 2090 to 2005. This is our baseline period, and we convert it to monthly data, and we use Aphrodite gridded data as the observed data, and that resolution was 25 into 25 kilometers, and we convert it to 5 kilometers. We use RCM data for average temperature and rainfall data, and we convert it to 25 kilometer RCM data, and we use DM data 500 kilometers, and we convert it 5 kilometer DM data. In for converting this process, we have used a IDW inverse distance weighting method. This is my methodology overview. We have for Aphrodite daily and Aphrodite daily data for rainfall and mean temperature. We convert it 25 kilometers, which is available, and we convert it 5 kilometers monthly data by inverse distance weighting method. For RCM data, which is 25 kilometers data, and we have converted to 5 kilometers RCM data in the same process. And for station data, we convert it to monthly data, and and then we for Aphrodite data, as we have converted to 5 kilometer data, we justified that data with Aphrodite, and to check our conversion process is accurate or not, and but and we found that our Aphrodite data and our station data, station observed data matched very well. And then we have created two models. That is, one is a multilinear regression model and one is regression model. And for multilinear regression model, we use Aphrodite data and RCM data for Aphrodite data and RCM data to create our model. And for regression model, we use only we use only one should only Aphrodite data. And then we validate this data by three we validate this data with three errors, that is MAE, RMAC, and R square. And we also calculate the lapse rate. Calculation of lapse rate for PLR. PLR means precipitation lapse rate, and TLR means temperature lapse rate. We also convert the DM data to 5 kilometer data from 500 kilometer data. We did this for taking all the variables in same resolutions, because for 25 kilometer approach data we are converting to 5 kilometer data. That is there is 25 kilometer RCM data and 25 approach data with the same. Then our main goal was to 25 kilometer RCM data will be converted to 5 kilometer data. And we did this for RCP 2.6 and 8.5. Now, PLR is precipitation lapse rate and TLR is temperature lapse rate. This is a 5x5 window. This is a approach data and DM data. We have this is 5 kilometer. Each of box is 5 kilometer resolution data. What we have did, that is for calculating the lapse rate, we use approach data and DM data. For converted 5 kilometer approach data and DM data for each box, for each 5 kilometer resolution, 5 by 5 kilometer resolution, we regression. We have regression with lapse rate with the two variables, that is approach and DM. And with this we have for example, if we want to calculate the X15 lapse rate, we need to use surrounding 25 values, and for surrounding 25 values means surrounding 25 lapse rate as approach data, and for digital elevation DM, that is elevation value. This is our multilinear regression model. Here we have seen that here 𝐸 is approach monthly data, and X1 is RCM daily data, X2 is lapse rate, A is coefficient of RCM, B is coefficient of lapse rate, and C is intercept. For each grids we have calculated for this is our model. 𝐸 is our model 5 by 5 resolution data for temperature and for precipitation, and its time scale is monthly value. This is our linear regression model. In this model, we have used only approach. We have used only RCM data for a dependent value, and sorry, for independent value, and lapse rate only that is monthly value. Only we have used only RCM value. And for validation, with three error indicator, that is MAE, RMSE, and R square. This is our model, which we predict, especially we predict the future value from 2021 to 2025, and this is the model which I've already discussed. That is our future model, projected monthly data. Each 𝐸-𝐫 is one grid, and time series from 2021 to 2050, and we use future RCM data for RCP 2.6 and 8.5. And we also use the average lapse rate from the model as our independent independent variables, and we have calculated the calculated coefficient from our model, from our baseline period we used, and we have also used intercept from our baseline period model. Now, as we converted 25 kilometer aprodite to 5 kilometer data, so we verify it by verify it with the station data. I have already shown you. We selected 2 stations. That 2 stations we verify how it matched with station data and aprodite data, and we have found that for temperature, for rainfall, we have found R-square value more than 0.8, and for temperature we have found 0.98 and 96, and it's a good result. This is the scenario. This is the here you see the for our baseline period from 1970 to 2005. This is the image of for each monthly period of our aprodite data. These all are graded data, 5 kilometer resolution. For a different month, it shows in different, and for also it varies from spatially and temporally also. This is for temperature, mean monthly 5 kilometer aprodite temperature for each month, and this is the average value from 2005 to 1970 to 2005, and this is for precipitation lapse rate. Here you see that precipitation lapse rate is different in different months, and also for spatial variation it also different, and for temperature lapse rate it also varies from place to place. Now we are checking the performance of our linear regression model, and here we have found that our MAE RMSC value are around 0.75 for monthly rainfall, and R square value is above 0.75, and for monthly mean temperature, MAE RMSC value is around 0.75 degrees Celsius per month for each grid, and for R square value, the grid square are above 0.75. For multilinear lapse rate model, we have found better than linear regression model. Just like here, the value is also better. Then just like MA value is 25 millimeter per month, RMSC value is 50 millimeter per month, and R square value is around 0.75. And also for temperature, MA value is 0.75 and R square value is above 7.5. Now we have calculated how multilinear lapse rate model is better than we have measured. Multilinear regression model is better than the linear regression model. Then we found that most grid multilinear regression model performed better for rainfall and for temperature also. Around 10% MAE and RMSC value, almost 10% decreased for rainfall, and for temperature, most grid also MAE value and RMSC value decreased by 10%, and for R square value also increased, and for rainfall and for temperature also most decreased. But for temperature, it shows there is not that much significant change for R square value. Very few grids has decreased, and very few grids increased also. We also check our model by box plot comparison. For box plot comparison here, Aphrodite data, linear regression model, and multilinear regression model. Here we have seen that almost for monthly rainfall, multilinear regression model shows it match with Aphrodite, which is our observed data. It matched good for inner quartile and also for extremes also. But for temperature, actually Aphrodite and linear and multilinear regression both are matched almost same. A little bit difference, that insignificant. And for extreme indices performance, we checked and we have found that for rainfall in our baseline period, 95 percentile a linear regression model and multilinear regression model, we have found that MAE value for a linear multilinear regression model is better, and for RMSE value also, where we have seen its low value for for linear for R square value, we have found that in both cases it's better, it perform better from linear from a multilinear regression from our linear regression model. And for fifth percentile, also fifth percentile MAE value, MAE value and RMSE value perform better than linear regression model, and for but for R square value, all linear model and multilinear model perform almost same. For monthly temperature, it shows quite a little bit different, just like for MA value and RMSE value. In both cases, multilinear regression is higher. That means it perform not good. And for difference is very very less. And for R square value, there is no significant change. And for fifth percentile, the scenario is almost same for MA value and RMSE value. Multilinear regression model perform worse than linear regression, and for R square value it is same. And we have also project our future for RCM 2.6 and 8.5. Our future period is 2021 to 2015. For rainfall, we have divided 3 seasons. MJJ is May, June, July. ASO August, September, and October. NDJFMA means November, December, January, February, March, April. We divide this season according to rainfall intensity. Here we have seen that in future, this area for May, June, July, in these 3 months, the precipitation will be decreased in maximum grades. That is 5 by 5 in 5 by 5 grid we have seen, and this picture are only for these images are only for 5 by 5 kilometer grids resolution image. And for precipitation in August, September, and October, northern part will receive more rain, but other region almost same, and also there are some reason the precipitation will be decreased by 2.5% also. And for November, December, January, February, March, April, we have seen that only very few grids in southern part, the precipitation will be increased, but for northern side, the precipitation will be decreased significantly. In some grids, they will receive the precipitation will be decreased up to 20%. And conclusions. 𝐸-state incorporated multi linear regression based statistical model performance is better than simple regression based statistical downscaling model for monthly rainfall and monthly mean temperature. Monthly rainfall has decreased trend in most grids. In the study area for RCP 2.6 and 8.5 scenarios. Sorry. Recommendation. Actually, in this study, actually, we have used only one RCM model. Actually, we can use more RCM model for validation, and I just downscale up to 5 kilometer in resolution. It can be do more than 5 kilometer resolution for local need. It is my recommendation. And also 𝐸-state 𝐸-state can be used to this 𝐸-state can be used also for predict the other climatic variable also. Thank you very much. That's all from my presentation.
Okay, thank you, Latif. It's a wonderful presentation. Hello, Qing-Fang, have you staying here?
Yeah, I'm here.
Hi, would you like to share your screen and show your presentation?
Okay, please, one moment.
Thank you.
Okay, can you all see my screen?
Yes.
Okay, let's get started. It's a great honor to be here today to presenting my research entitled One Parameter Beautiful Model for Water Balance Captures Emergent Behavior in Darwinian Hydrological Model. And now let me take a brief introduction of myself. My name is Fang Qingqing, and I graduated from Beijing University to get my PhD degree at the beginning of the year, and now I'm doing my research at North China Electronic Power University. So let's get started with my research. At the first paragraph, the research background. As all we know, the climate change and the human activities have changed the ecological system a lot, such as reducing runoff, vegetation greening in most part of China, even in the northeastern of China, which is way too much lack of water resources. But however, there are a complex relationship in it, such as, for example, the climate change, especially the global warming could cause a vegetation greening, and furthermore, vegetation greening will also cause reducing runoff and making arid area drier. So how can I relieve the reducing runoff and make the eco-hydrologic system more better? So let's talk about the relationship between the three index, the climate change and the vegetation pattern and hydrological process. The climate change triggered the vegetation pattern and hydrological process, and these two things had a dual regulation between them. So let's talk about the hydrologic process, the detail. The precipitation partition is one of the most important hydrologic process, and we can partition it to two main components. The first is runoff, the second is evapotranspiration, and also the evapotranspiration could also related to vegetation patterns. So we can correlate the hydrologic process and the vegetation pattern with that important index. And now a few literature talk about the competition between runoff and evapotranspiration, because when the precipitation is limited, so we can see they are all increased in infinite conditions. So that's our question. The first one is, shall we find a relationship between vegetation, climate change, and the hydrological process at certain scales? And second, shall we get the vegetation threshold value that could keep the balance between reducing runoff and evapotranspiration? Now we have select a study domain which located in the Inner Mongolia province of China, and its Halara River Basin. So there are three reasons why we choose this area. Because firstly, it's sensitive to the climate change, and the second, it had abundant vegetation resource. Third, it's a semi-arid area which had a very severe water shortage. And then, based on the water hydrologic stations, we separated the basin with 6 sub-basin. And next, let me talk about the method. Firstly, we used the beautiful framework to solve one of them. For the beautiful framework hypothesis states the ratio of actual evapotranspiration is fundamentally related to the ratio of potential evapotranspiration, and then we can get the relationship between evapotranspiration, precipitation, and the potential evapotranspiration. So we can get the boundary limiting condition, as you can see. And then we use the two-stage partition theory to partitioned precipitation into soil wetting and the direct runoff. And then we use a new index, that means initial evaporation, we called E0. It's a new index that occurred due to vegetation interception and the water storage in topsoil, and it cannot take part in the competition with runoff. And then we used a generalized proportionality hypothesis to get our new equation, and we set a new underlying surface parameter eta to in the equation. This underlying surface parameter is correlated significant to the basin vegetation coverage. Second, we use another theory, two-stage partition, to get the relationship between evaporation, precipitation, runoff, and the soil wetting. And we could get two form of this. The first one is the normal form, and the second one is the dimensionless form. And we can get for a classical index, the Horton index, the base flow component, the evapotranspiration component, and the runoff components. And then if we want, we would like to get the relationship between vegetation and the basin, we should get the solution of the NAMNA. So we get two solution of this. The first one is generalized, the second one is dimensionless. This is the derivation of our equation. Then we can get the performance of the two-stage partition model. We can find the performance is significant better than that in the 611 bases in USA. So that's had a good performance. And the second, we get this four equation with dimensionless, and we find the coefficients of determination are higher than 0.98. So it's a great great performance. And we can see either you can use it in between basin data and or between year data. They show the same patterns. And then we find the significant relationship between vegetation cover and the NAMNA. And they had a negative relationship, and the coefficient of determination is 0.85. And if you add another index MTB into this equation, we can find that we improved the correlation to 0.95. The MTB is the average, the interval between two rainfall events. And then we can get the ecohydroclimatological model from our study, and the four classic index, and beside we can get the continuing in vapor transpiration with the NAMNA. So, and the NAMNA we can assume it's related to the vegetation coverage. So that's the only one parameter of these things. And then we need to talk about the threshold value of vegetation. Let me take our hypothesis. Let's trace back to our question 2. So shall we find the thread value of vegetation that's keep balancing of runoff and the continuing evapotranspiration, or we hypothesize this competition between them, and the continuing evaporation and the runoff will increase with the potential evapotranspiration and precipitation. But because of the global warming and the increased rate of the evapotranspiration, the rate of it will exist of the rate to the rate of runoff. So we could find the inflection points that's between runoff and continuing evapotranspiration, and then we could see the vegetation coverage should less than 0.73, and that would keep the runoff not going to reducing. So that's our summary. The first, we built a new ecohydroclimatological logical model. Second, we quantify the competitive relationship between runoff and the continuing evapotranspiration. Second, the third, we find the vegetation threshold which could keep the balance between runoff and evapotranspiration. Okay, that's all. Thank you.
Yeah, thank you, Chin. That's an excellent presentation. Yeah, I would like to request you to unshare your PowerPoint presentation, or can you stop sharing?
Okay, okay.
Yeah, thank you. We received the email from Mr. Manish that he will not be able to make a presentation, and Professor Arup Kumar Sharma or Paswati, if you are online, so can you unmute yourself? Okay, I think he is not online. Probably some internet connection issue. Okay, we have had 4 presentations. So now I would like to open the floor for questions, comments, and any kind of suggestions for the improvement of these studies presented by 4 presentations. If you have any question, then you can unmute your microphone, turn on your video, and you can directly ask to any of the presenter. Or if you want to put your questions in the chat box, that is also fine. I will pick up the question and then I will ask to each presenter. So let me just summarize that we had 4 presentations, one from Professor 𝐕𝐢𝐫 𝐁𝐍𝐵. He presented about the contribution of the base flow to non-point source pollution in agricultural watershed. The second presentation was from Ms. Wang Libo about identification of the factors of influencing factors for the evapotranspiration in cold and semi-arid region. The third presentation was from Mohammad Latif Hussain. He presented about this statistical downscaling of climate data sets under heterogeneous terrains. And the last presentation was from Chin. She presented about this one parameter Goodokyo model for water balance capture emergent behavior in Darwinian hydrological models. I think all of the presenters are here. Now I would like to open the session for questions, comments, and suggestions. Okay, you can unmute your microphone. You can turn on your video and you can start asking questions. You can raise your hand. Okay. Yeah, Sela. You can introduce yourself. Okay, and then please be specific to the presenter to whom you would like to ask the question. Okay. Yeah. Thank you.
Good morning, professors. Good morning, everyone. I am Shela Talampas, PhD, first year PhD of WEM. I'd like to ask a question on the first presenter, Professor Professor 𝐕𝐢𝐫
𝐁𝐍𝐵, yeah.
𝐕𝐢𝐫. Professor, since reliable estimation of bare flow non-point source pollution can encounter some uncertainties, which do you think, based on your study, represents the largest uncertainty source in base flow non-point source pollution estimation?
Yeah, Professor 𝐁𝐶, are you there? Okay, I did not see him. Yeah, he's here. Professor 𝐕𝐢𝐫, are you there? Okay, let's skip this question. Probably he will come back. So any other questions from other participants? Sela, I will contact Professor Baolin from my WeChat account. So please keep this question probably a little bit later, okay? Yeah.
Thank you, Professor.
Dr. Locke.
Hi, okay. Hi, good morning, everyone. I see that Vishal also raised his hand. Maybe we should give priorities to our students. Vishal, maybe you can start first.
No, sir, you can ask, then after that I will, after your
Yeah, I'm
question.
here. Excuse me?
Okay, yes. So Professor Baolin is here, so maybe we can take this later. Professor Zangam, I think we should pass the floor back to Professor Baolin.
Professor 𝐬𝐫𝐿-𝐁𝐍𝐵, that was a question from Sela. I'm not sure whether you could hear her question.
Oh, I'm sorry, I missed that.
Okay, Sela, maybe you can ask questions to 𝐬𝐫𝐿-𝐁𝐍𝐵, Professor 𝐬𝐫𝐿-𝐁𝐍𝐵 again.
Okay, Professor 𝐬𝐫𝐿-𝐁𝐍𝐵. Since reliable estimation of bare flow non-point source pollution can encounter some uncertainties, which do you think, based on your study, represents the largest uncertainty source in base flow non-point source pollution estimation?
Sorry, I didn't follow you.
Okay.
Please say it again.
Okay. Can you hear me, Professor?
Yeah, okay. Yeah.
Okay. Since reliable estimation of bare flow non-point source pollution can encounter some uncertainties, which do you think, based on your study, represents the largest uncertainty source in base flow non-point source pollution estimation?
Oh, okay, you mean which is the most uncertainty, right?
Yes, Professor.
Yeah, okay, that's a very good question. Thank you very much. Yeah, actually, as I said in my report, that there is no definite method which can be used to measure the base flow. As we know, yeah, of course, we can use the chemical method, but usually in hydrology we do not use this method actually, and especially for the large area like our in the watershed scale, the business scale. So there is actually no definite method. So in this case, we use the digital filter method, but this method, as I say, we cannot use the observation method to validate it, and this is one. I think this is one of the main uncertainty comes from. And another one is that because we are more interested in the spatial temporal changes of the non-point source pollution over a basin scale, so I use the SWOT model method to explore this topic. As we can see from our results, we actually use the digital filter method to verify the results for the SWOT model. Actually, I think the main problem in our research is that how can we find enough observation results, for example, by the chemical method, to validate our results over the basic scale. I think this is the main problem of our research, or the main uncertainty come from.
Thank you, Professor.
Yeah, okay, thank you very much.
It's clear.
Yeah, thank you.
Thank you.
Yeah.
Thank you, Professor 𝐬𝐫𝐿-𝐁𝐍𝐵. Maybe we can go to another participant. Vishal, you would like to ask any questions to any presenters?
Yes, sure. Hello, everyone. I am Vishal Thakur, currently pursuing master's degree in Asian Institute of Technology, and I am in second year now. So I have certain questions from few presentation. First, I want to ask from Latif Hussain. Can you go to the slide number 8? Latif Hussain. Can you hear?
Yes.
Yeah.
Which slide?
Slide number 8.
Yeah, Latif, can you share your screen? Okay.
Yeah, sure.
Please.
Yes.
So in this figure, like when we are estimating the lapse rate, so for
Yes.
finding the value of X15, we are considering 25 blocks, right? So what
Yes.
we will do with the 25 blocks, whether we are averaging it or we are following some other method?
Actually, we have done 25. This 25 that is called multi-linear regression. Actually,
okay.
You understand? Each variable has different value, and each one has multi-linear regression have done for this only to determine this one, and for consecutive this one we need in this this one for this we have this entire this that is x2 to x2, x3, x4, x5, and x6. This blue shaded window. For each value, we have to calculate. All these variables will be taken.
So you calculate separately. There is no reason
Yeah.
to the.
For each grid, I calculate separately.
Okay. Thank you.
Yeah, thank you, Latif. Yeah, Bisal, do you have any other question?
Yeah, one more question I have from King presentation.
Yeah, Latif, can you stop sharing your slide? Okay, yeah, please.
Yeah, since the slide number is not mentioned, so I was not able to highlight that. So it was in the method section. King, can you? I think she's unavailable.
Yeah, you can go to next question, Bisal.
Yes. So from my side, this was the question, sir. No.
Okay. If Chin joins, then I will call her again. So, yeah, Dr. Locke, I saw you raising hand before, right?
Yes, Professor Sangam. Actually, I have one question for Chin as well, but since she's not here, I will come back to that question later. Can I again, sorry, bother Professor Pauline?
Yeah, sure. Yeah.
Yes, because that's very exciting presentation, and during my previous affiliation, I also did something similar.
Yeah.
That we look at the rainfall derived runoff. If you're working with base flow, then you should know that stuff, right? Rainfall derived infiltration and inflow. So after the rain, there is a slow rising limb of the water slowly seepage into the soil before it convert into the base flow. And I have observed that there is a very significant implications of the soil type, the landscape, and also the spatial and then the temporal as well, right? So I saw that you had mentioned somewhere that you find the correlations between the pollutants load between the base flow and the runoff. So which makes me very curious, because if before the runoff transform into the base flow, it has to travel through the soil, and the soil should not be uniform, right, across landscape. So what would be your explanation where you can detect that correlation between the pollutant of runoff and the pollutant of the base flow? So that would be my question.
I'm sorry, but would you please explain your question again?
Okay, so I remember that you mentioned that you have detected a correlation, right, between the pollutant on the runoff and the pollutant of the base flow.
Yes, yeah.
Okay, so because through various models practices, of course, it will be impacted, but from a basic physical point of view, the runoff, it will infiltrate through a soil, right? So the soil should be different from one landscape to another, right? So then how come pollutant in runoff will be similar or correlated with the pollutant on the
So your question is about the relationship between the soil type and the base flow?
No, my relationship is what would be the explanation why there is a correlation between runoff pollutant and base flow pollutant, because soil type is another source of heterogeneity. Yeah.
Okay, you ask me why there is a close relationship between the base flow and the total runoff, right?
Yes,
because the base flow should be from the soil, right?
Yeah.
Okay. I get. Yeah. Okay. Yeah. Sorry.
Sorry. Yeah.
Yeah. This is very interesting question actually. Actually, this is a very small watershed, I said, and actually, in my other researches, I investigated the relationship between the base flow and the total runoff for very large areas. I also explored the relationship between the base flow and the total runoff, of course, including the polluting loads. And I found that for not only for this small watershed, I mean a small basin, but also for a very large basin, there is a very close relationship between the base flow and the total runoff. Actually, in my imagination before this research, I imagined that okay, for very wet areas, I mean for example in southern China, and for large basins, the relationship between the base flow and total runoff would be very close. It makes sense because the main contribution for the total runoff should be from the base flow. I mean, especially for a large area, a large basin. This is a normal imagination, and as you say, for example, because for a very large basin, there are different types of soils, especially different landscapes. But actually, especially for the dry season, for example, in winter, because the total runoff was not decided by the runoff, but by the groundwater. So actually, the water quality is not mainly decided by the soil infiltration actually, but actually by the groundwater. So I think this is the main reason which can explain your question. But actually, as you asked, I was also very surprised that the base flow for a very small basin, actually, for example, in my presentation I talked about just now, the base flow also contributes a lot. So this is very actually it was a little bit surprised me after the exploration of my research. I suppose the main reason was that there was actually there is the rainfall in this area is not so large, and this basin was near the sea. I mean, it is a coastal basin, so the groundwater actually contributes a lot to the total runoff. So I think that would be the main reason, not only to answer a question, but also to explain why the water quality is mainly decided by the base flow.
Yeah, agree.
Yeah, I think I can explain clearly. Thank you.
No. Actually, it's a very good response, because so basically, what you try to say is the pollutants or the water quality is somehow decided by a boundary factors already. So they are not affected by that much by the rainfall infiltration processes. So that's why So that's why the correlation are somewhere fixed already. Okay,
Yes,
so that makes sense. Yeah. Okay. So thank you very much.
Okay, thank you.
For
Thank you for
good,
question.
yes.
Yeah.
Thank you, Professor 𝐕𝐢𝐫-𝐁𝐍𝐔. I have also a couple of questions, but yeah, I would give priority to the other participants. I saw hands. Okay, Suhas, please go ahead. Suhas, you are muted. Can you unmute yourself?
Okay. Hello, everyone. This is Ms. Suhas 𝐬𝐈𝐓. I'm research associate in WEM working under Professor Sangam. And I have few comments and questions to Mr. Latif Hussain. So if he is here,
Yeah,
can you please hear
Latif
me?
is here, yeah.
Sure. Okay. Since you have developed two different models and validate the result with YAMAE and RMSE, if I'm correct, then there is the value of YAMAE and RMSE are around 20 mm and 50 mm for precipitation.
Yes.
So if the observed precipitation is around 150 mm according to the graph, then how would you justify this this much of RMSE is a good result? Is there any standard to justify the results? This is my first question. And the second question is, rather than question, it is a comment. Rather than justifying the result using these statistical indicators, why haven't we compared the result with pre-established methods like empirical quantile mapping for statistical downscaling? So, or any other methods, if you have compared, then I think the results would be much more effective, so that the other researchers can utilize this particular method based upon the result, like either it is performing better than the pre-established method, or if it is not performing, then we could have extend the research in a new direction. So that's my comment.
Yeah, thank you, Suhas. Actually, there is one question, right? And then one comment. Probably, Latif, do you want to respond to the first question?
Thank you. Actually, what you have told, it is right. Actually, we have developed two models. That is, one is linear regression model and one is multilinear regression model. Actually, the linear regression model is a simple model that is usually used by the nowadays. But for multilinear regression model with a lapse rate, which is incorporated in multilinear regression model, it is a new thing. So we just compare with the present situation and the newly developed model, and we have found that it is performing better. Here you have seen in this slide number 20. How much it improved, we have checked with this model. This is actually our main standard. We have what we have did, and for your comments, actually what you have told, it is right. Actually, it should be validated by other parameter also. Yes, I'm agreed with you. Thank you. Is there any other? Are you satisfied?
Yeah, I have other two questions also. Maybe this is from the other other participants.
Suhas, maybe I can repeat the question again.
Okay.
Latif, can you go back to the same slide you have shown? His question is related to this 25 millimeter per month, RMSE, also the mean absolute error, right? So do you think that this 25 to 30 millimeter or 50 millimeter of rainfall per month is acceptable or not? So that's his question.
Yes. Actually, I didn't actually measure this with the other standard, but it should be checked. I didn't check with the other research that what how this value is it standard is good or good enough or not, but I didn't check, but I just checked with 2 models which I have developed, and with these 2 model I differentiate, and I just told my recommendation is multilinear is performing better than linear model. Actually,
Thank you.
it is not.
Yes.
I don't think that is there any standard is there or not. I am not sure.
Right.
Other research also. Thank you.
Yes.
Sir.
Yes. Yeah. Thank you, Latif. If you have rainfall of 1,000 millimeter a month, then this plus minus 50 millimeters should be okay, right? But it's not outlined here.
Yeah. Yes.
Anyway,
Yes.
Thank you.
You're right, sir.
So yeah, any other questions from other participants, or Suhas, do you have any more questions?
For 𝐕𝐢𝐫-𝐁, if the presenter is here.
Yeah, I think she is here. Wang, are you here? Yeah, she is here.
So besides temperature and precipitation, what might be other factors for change in evapotranspiration? And how can we be assured on these factors only, since the precipitation and temperatures were majorly discussed in this research? So unless there are other factors, what could be the proportion of their impacts in the evapotranspiration?
I'm sorry, I can't follow you, please. Could you please say it again?
According to the research you have presented here, so you took temperature and precipitation as a factors, and the result says that they have significant impact on the evapotranspiration. But if any researchers are interested in other factors also, what could be the other factors, or if there are other factors which could impact the evapotranspiration? And unless there are other factors, if there are other factors, then what could be the proportion of impact, like the impact of temperature, the impact of precipitation? What could be the proportion of the impact on evapotranspiration?
Yeah, maybe I think in my study I just use the I use a calculate to
李波，你听清他的问题了吗？
我没太听清，我这边。
Okay, I will. Maybe I can translate the question into Chinese for her.
Translate in Chinese to understand.
Yeah. Okay. Professor Sangam, I will translate to him. To her. 他问的问题是什么呢？就是说想问一下，那么在你这个区域里边有哪些因素也会有可能会影响蒸散发？那么怎么影响的？就是其他的一些因素，像气温呢，会不会有可能影响这个蒸散发？就这个意思，就是你就说一下有没有其他的因素影响？那么其他的因素起的作用有多大？你跟他说一下就行了。
好，我刚才要跟他说这个，就我里面其实讲到这个了，我分享一下我的这个屏幕。好，谢谢老师。In my study, I have in this picture, I have calculated about 7 factors, which maybe influence the evapotranspiration, and it's including the precipitation, temperature, and NDVI. And after that, I find the precipitation and the temperature have the highest influence to the evapotranspiration. So, based on the study, I focused on the temperature. In this picture, I have in this picture, I make the cooperation influence about the max temperature, the mean temperature, and I use the duration temperature to calculate the influence to the evapotranspiration. So in my study, I find there maybe have 7 factors will influence the evapotranspiration. But in my study, I focused on the precipitation and temperature because I make this picture, and I think they have the they are the most important factor to the evapotranspiration.
Okay, thank you so much, because I found that maybe I have missed this portion, because I thought that you presented only 2 of the variables, but here are like 5 or 7 variables. And in the next slide, I have another question also. So you have shown that there is change in trend in growing and non-growing season. Can you please explain what might be the possible reasons behind the just opposite change, opposite trend in growing season and non-growing season? Because I find that the trend is exactly opposite. What might be the reason behind it?
Yeah, I use the growing season and non-growing season because the vegetation in this area have the in different season, the vegetation is different, and in this part I only focus on the precipitation and the temperature, and the temperature can influence the vegetation very. I think the influence is very strong. So I depart the season to the growing and non-growing, because if the vegetation is because if we don't have the vegetation, or the vegetation is decreased, the evaporation, the transpiration will decrease, and you know, the evapotranspiration is cooperated by the evaporation and the transpiration. And I think in this 2 parts is different parts, and the vegetation is the have the most important influence in this part. So I depart the 2 seasons.
Yeah, no, I clarify the question again. My question is not like why you distinguish between non-growing and growing season, but my question is, have you find any reason behind just opposite trend in growing season and non-growing season? Because as far as my understanding, I might be wrong also, that when the plants are in growing state, then there is much more transpiration, and transpiration is has high proportion in the whole evapotranspiration terminology. So that is my curiosity. What might be the underlying reason? Okay, we see the results. Yeah, whatever the results is, there is downtrend in growing season and uptrend in non-growing season. But what might be the underlying reason behind it? That's my curiosity. So if you have experienced it, can you please share it to us?
I think
maybe someone could please translate in Chinese.
Yeah, Professor 𝐕𝐢𝐫, we need your help. First, maybe Wang, you should clarify what is the meaning of this growing season and non-growing season, right? So the growing season is it agricultural field, and you have crops there, and non-growing season is like there is no crop there, right? So is that the meaning, or it's like forested?
Okay, I see. Okay, just wait a minute. 立波，你是这个 growing， 你的这个 non-growing season 是几月到几月啊
？5月到non-growing season，那个10月到次年的4月，是为什么分是吧
？10月到次年4月，不是，他问你这个分可能没有很大的意义，你知道吗？你能回答这个问题吗？
就是说分这个季节没有很大的意义是吗？
对啊，你这冬天可能就没有正产发了，不是吗？你这个草地，对吧？
对。
Okay, I just talked with her, and maybe maybe your question is about why should we divide to growing season and non-growing season, right? And okay.
First is like what is growing season and non-growing season, and why there is totally opposite trend in.
Okay, yeah, okay. Yeah, actually, I talked about with her this figure, and yeah, I think you are probably right, because this basin was mainly dominated by its grasslands, and we have the grasslands. The grasslands is deciduous during the winter. Actually, very because this basin is located in the northern part of China. The growing season is around mid to maybe late August or early September. So maybe there is no much meaning. It's not so meaningful to use the data from the non-growing season, because we have only the evapotranspiration here is mainly from the evaporation from the ground or the soil, but it would be very, very small. So I believe, for example, from the subclimation or something, from ice or snow. So I think this may be the reason why we have different relationships here. Because in the growing season, the evapotranspiration was mainly dominated by the transpiration, but during the winter, mainly from the ice or snow. Right? Yeah. I think maybe this is the main reason here.
So this basin, this basin has snow effect. So there is snowfall in this basin.
Yeah, because in this part, I only focus on the change of the diurnal temperature. Because of the climate change, I think the temperature is higher than before, and the diurnal temperature is is growing. So
actually, maybe
in winter,
maybe one possible reason. Okay. Yeah. Okay. Maybe I think from her figure, I think one possible reason would be that in this basin, the main contributor for the evapotranspiration, I think you should also include the soil water content. We have the negative relationship between temperature and ET, right? So I think this figure actually indicates there is another contributor maybe here.
Okay.
Right. Yeah. Thank you, Professor Baolin.
So I think, Can you hear me?
Right. Yeah, Suhas, you understood the explanation, right? So yeah, and probably please look at the scale also. The y-axis. In the growing season, the maximum is about 550 millimeter, right? Non-growing season is about 250 millimeters.
Yeah, very small.
Basically, the how the change in temperature influences the evapotranspiration, right? So because of the nature of the land use and also the climatic conditions, probably it's possible. Yeah.
Yeah, I think so.
Okay. Yeah. Thank you.
Thank you. Thank you for your proposal.
Thank you very
Right.
much.
Yeah, we are almost at the end of the session. Yeah, any more questions to the presenters? I would like to take one more question from the participants. Yeah, Pianuts, yeah, please introduce yourself and you can directly ask questions to the presenter. Yeah, please.
Hello everyone, my name is 𝐕𝐢𝐫-𝐁𝐍𝐔, PhD student in AIT. I would like to ask a question for Professor Baolin, the first presentations.
Sure, sure. Yeah, okay.
I think your research is already identified the problems about non-point source pollutions for agriculture activity in China. So I would like to know about what is the solutions or mitigations measure for minimize this problem in China?
Sorry, I didn't get you. What's more?
What is the solutions or mitigations measure for minimize this problem?
You mean
in China?
You mean the possible solutions for that?
Yeah,
right?
Yeah.
Yeah, okay. Yeah, very, very hard question for me, because the non-point source pollution is very, very serious problem. Actually, I can take the watershed, I mean the basin I presented as example. Here, generally in China now we have many policies or managements on the point source pollution. It is the point source pollution. Generally speaking, in most basins, I mean in most areas of China, the government has taken many policies. I mean, it's accept many different the laws, the economic encouragements to deal with the point source pollutions. So now the pollution of China is mainly caused by the non-point source pollution. Now, as to this problem, actually we have go to this watershed, go to this basin, talk with the farmers of this within the basin, and we talk with them, and we said, oh, you have used the fertilizer much more than should be used. The farmers they do not have much knowledge on how much fertilizer they should use. So usually they used much more than what is actually needed in this basin. So as to your question, my answer would be that, okay, in this case, maybe we cannot stop them from using the fertilizer. It is impossible, for us. But we can give them some suggestions on how much fertilizer they should use, to get probably the same crops within this basin. I think this is what actually, which is the practical suggestions for this basin, maybe, and I think for other areas too.
Yeah, thank you, Professor Baolin.
Okay, okay.
Yeah, Miss Pianuch is also AIT-BNU. I think she's supposed to be in Beijing with all of us, but I'm sure after this travel restrictions are over, she can travel to your university.
Oh, that's good.
Yeah, this is also a very important question because, the watershed that you have investigated, most of the non-point source pollution source is groundwater, right?
Yeah.
So probably it's very difficult to, manage this non-point source pollution coming from the groundwater. So I think, there must be very careful or very, good way of asking the farmers not to use the more fertilizer, or even they use. Probably there are several other, techniques like slow fertilizer, or how can we reduce the leaching of those fertilizers and so on, right? it needs different kind of innovative, techniques to reduce the leaching and other pollution into the groundwater, right?
Yeah.
Thank you, Professor 𝐕𝐢𝐫𝐤𝐬𝐡𝐨𝐷. I think.
Yeah, thank you very much.
We are almost 10 minutes, behind this schedule. So probably I can wrap up. We had very interesting presentation from 4 presenters, and most of the presenters presented the modeling of these, hydrological responses and water quality in the several watershed in China and also the Thailand. I think this will add some, value to how do we understand the hydrological phenomena under the context of the climate change and also under the, water quality management, right? So those presentations were very, very, important and also the useful. So I would like to thank all the presenters who presented the interesting results of their research. And also I would like to thank all the participants who attended this session. So let's give a big round of applause to all the presenters. Okay.
Thank you.
Yeah, and we have another session after the lunch time, which will start from 1 p.m. of Bangkok time. Again, there are 2 sessions. We have a parallel session, right? One session I will be chairing again. And then another session chaired by Professor Wu. I will be chairing the session on interactions of water resources and ecosystem. And the professor will chair the session on risk assessment of ecosystem degradation in changing environment. Okay. So with this, I would like to thank Messi to co-chair this session also. And let's come back before 1 p.m. Bangkok time. Okay, before 1 p.m. Bangkok time. Okay, thank you, everyone. Messi, do you have any announcement to make to the participants?
I'm afraid no. I don't have any idea.
Okay, so thank you, everyone. So let's meet before 1 p.m. Thailand time. Okay, so thank you very much and see you later. Bye.
See you.
Hey, thank you all. Thank you. See you later.
I think the next conference in this Zoom link is 2 o'clock in Beijing time and 1 o'clock in Thailand time.
Right.
Everyone would like to attend this meeting as well.
Yeah. Thank you.
Thank you. See you.